All right, everyone. Well, welcome back. We're going to look at implementing our own queues. So we're going to look at this QADT, the abstract type, so the abstract data type for the queue, and we're going to implement just the classic operation. So we're going to have enqueue, dequeue, first, is empty, size to string. This is a little confusing because this doesn't map onto the Java collections interface, right? It's not the same. They do basically the same things, but the names are different. And we're just doing that because these are the classic names for the operations. All right, enqueue, dequeue, first, is empty, size to string. All right, so we're going to use this. We're going to implement this. We're going to implement it in a couple of different ways. So here is our interface that we're going to implement, this QADT. That's what we're going to call it, and we're going to use generics again. Enqueue takes in an element you're going to stick in. Dequeue returns the element that you're going to get out. We're going to have first that returns the element but does not remove it from the queue. It's like the peak, remember? Is empty, of course, tells you if it's empty. It has a Boolean. We have the size, which is obvious, and then the toString. All right, so the first way we're going to implement this is with linked lists. So linked lists for stacks were very simple, right? It kind of stacks and linked lists look a lot alike in some sense. If you have a front reference, then you add and subtract from the front reference. But queues are a little different, right? So queues require that we add to one side and pull from the other side, right? We add to one end and we pull on the other end. So when we implement this with a linked list, what we're going to need to do is we're going to need to have a reference to the first thing in the list, and we're going to have to have a reference to the last thing list. I mean, we don't have to, but if we don't, then every time, so going back to our discussion of orders, right? We talked about the orders of operations. So if we implement it with one front reference, then the order of dequeue would be order in, right? Because we would have to start from the front. We'd have to go through all the elements in the queue to the very end, and then we'd have to remove the last one. So we'd have to iterate through in references, right? If there's in things in the queue, we'd have to go through all in of them until we got to the one of the list. We got to the one at the end, and then we'd have to remove it. So that is not ideal. We don't want it to be order in. We'd like it to be order one. Order one is way faster. So the way we make it order one is we actually keep two references. We have one in the front and we have one for the rear. If we want to add things, we use one of them. And if we want to remove things, we use the other, right? So two references. And remember, that changes it from order in to order one. All right. So when we want to add something, we're going to add an element to the rear of the queue. In fact, it doesn't matter. It's up to you. If you define the rear to be the front of the queue or the front to be the front of the queue, it's up to you. In this case, we're going to add elements to the rear, which keeps the nomenclature clear because the front of the list is the front of the queue, and the rear of the list is the rear of the queue. So we're also going to keep a count. And so what we're going to do when we add something to the rear, we're going to have a pointer to the last element. When we want to add something, of course, it's just a linked list. So what we're going to say is we're going to say rear.next equals new thing dot.next equals null, and then we're going to say rear equals rear.next, right? And that's going to set the next pointer of the last element to be equal to the new thing that we're adding. We're going to make sure that that last element, that new element, that the reference is null. Maybe we've done that somewhere else in the constructor or something. It's up to you, but it needs to be sure that it's null. And then we're going to say we're going to move the rear from the old rear to the new rear, right? And that's how we implement. If you think about that, that's order one. It doesn't matter how many things are in the queue. We can always add to the end of the queue by just using the rear pointer. If we tried to use the front pointer and we didn't have that rear pointer, we'd have to have a loop, and we'd have to go through until we found the end, and then we'd have to add to the end. We'd have to find it first and then add. But if we keep a pointer to it or a reference to it, whichever one you want to call it, then we can always find it, and it's an order one operation. Okay, so the implementation in this case can dictate the order of the operation for the queue operations. Ideally, queue operations should all be order one, right? But if you implement it incorrectly or you implement it badly, it could be order n or whatever it is, order n. All right. So removing from the front, and notice also that we increment the count. So removing from the front, again, it's just like removing from the front of a linked list in the stack. We just say element to remove equals front equals front points to next or dot next, and then we're like done. We decrement the count, right? That's all we have to do to take it off the front. It's just like the case with the stack. All right, so let's look at the code for this. So here we have our linked queue, which is going to implement the queue ADT. So it's a linked list implementation of a queue, and it's also a generic. We're going to have a count, and we're going to have our linear node inside, which has a head and a tail. Okay? So here is our linked queue. We initialize it by setting the count equals 0. We said the head equals the tail equals null. So everything is null to begin with. Super straightforward, right? All right, so when we put something in the queue, we are going to take in an element. And remember, this is the case, this is the linked list where you have the linear nodes, and then the linear nodes have a reference to an element, and the element type is the generic type. Okay, so we're going to have our linear node T. We're going to make a new one, and we're going to pass in the element that we're trying to enqueue. So we're going to make a new one of these linear nodes, which is our linked list structure, and it's going to contain the element that we're trying to put in the queue. So if it's empty, we're going to say head equals node. So if it's empty, head equals node, right? So else, if it's not empty, so this is the case that there's nothing in there, which means the head of it is going to point to the only thing that we have, which is this one. Else, we're going to set the tail. We're going to say tail.setNext node. So we're going to add this to the end, right? So we're going to have to, if it's empty, if there's nothing in there, that means the head and the tail are both null. So we're going to have to set the head equal to the node, right? Because otherwise we're not going to be able to remove things from it. Then we're going to set tail.setNext equals node, right? Which means the last thing. So if it is empty, then tail is null, and so we can't do that tail.setNext node, right? Because that's going to be an invalid operation. You're going to get a null reference problem, and it's going to crash because that thing is going to be null right there. You're going to get an exception. So if it's not empty, we're going to set the tail. Basically, remember, we got a reference to the last element. We're going to set the next element from the old last to be the new thing that we're going to add. Then we're going to say tail equals node. So we're going to move that tail pointer down one in the list to the new tail, actual tail. And then we're going to increment the count. All right? All right, so let's say if we want to remove things. How do we remove things? So if it's empty, we're going to throw this exception, this empty collection exception for the queue. Otherwise, we're going to say get the result. We're going to get the element out of the head node, right? Remember, we're not going to return the node back. We're going to return the thing that's in the node back. All right? Then we're going to say head equals head dot get next. So what that's going to do is we're going to get the element that we've stored in the head out. So now we have a reference to that. Then we're going to take the head and we're going to make it equal to the next thing in the list, right? It's going to go forward one, and then the old head is going to have no references anymore, and it's just going to automatically deconstruct itself, right? So then we're going to decrement the count because we just took everything out. If it's empty, so we have a special case here. If it's empty, we have to set the tail equals to null. So remember, this is a special case we have to take care of. There's actually some ways to get around this, but in this case, we're just going to leave it like this. We're going to say if it's empty, we're going to let the tail equal null, and then we're going to return the result. All right? So this is a nice, hopefully this is clear to you how this works. Because remember, the case of the head being, the case of the queue being in the state that the queue is empty, the head should be null and the tail should be null. So let's go back and look at this. If we say head, let's say there's one element in the queue, one node in the list, right? So what we're going to do is we're going to say head equals head dot get next. So head dot get next, because it's the last element in the queue, head dot get next should return null, right? So the head's going to be null, count minus minus, so the count's going to be 0. The only thing that's broken at this point for an empty queue is that the tail needs to be null. So we take care of that here. We say if it's empty, we're going to set the tail equal to null, and they're going to return the result. All right. All right, so that's the end of the lecture. That's how we implement queues with a linked list. In the next lecture, we're going to look at how you implement them with arrays. Okay, thanks.